This was close.
Ladies and gentlemen, today we're going to start with the electrical potential. Electrical potential basically is volt, V-O-L-T, stuff here. So we like to start with the section 20.3. The section 20.3 is talking about charges. Electrical charges has electrical field, and because of electrical field, they have the electrical potential as well. The electrical field and electrical potential is perpendicular to one another, so that they basically, after you find out the electrical field, you can get the information about the potential. So now is talking about a charges. Suppose that there's a charges in here, it's called Q. So here is from point A, in which case is in here, point A to point B. In which case is here is point B. This path is not. The path is not necessarily continuous, not necessarily a smooth line or straight line, can be any curved line. So from here, there's an RA we're talking about, the vector form RB we're talking about here. So we have an arbitrary point we're talking about here is R. And in these cases, there's a ds in this direction. And there's an angle between here and here is an angle theta. And around this direction, in which cases is the unit vector, it will be dr. So from the potential, the voltage or electric potential from point B, point A to point B, we written as from the previous section, V sub B minus V sub A is equal to minus integral from A to B, and then E dot ds. Okay, ds, E is in this direction, and ds is in this direction. So with angle. So electrical field and motion have an inclining angle. So that we have to do the mathematical manipulation in order to getting more meaningful information. So one thing we like to say is minus A to B. If it's E dot ds, in which cases is equal to E times ds times cosine theta. Okay, so the angle between them is theta. The dot product is equal to cosine theta. And then what is the electrical field? The electrical field, because this is a charge, so it's related with force per unit charge. It's a force per unit charge. So that from A to B is the case of E Q, in which case is capital Q divided by R squared. And then that is equivalent to dr. So from this point of view, then we can do the integration. When we do the integration, this is r squared, this is minus. Then you will minus 2 plus 1, and that become -1. So KEQ integral of RA to RB, and then that is equal to dr divided by R squared. So based on this simple integration, then you will get the following important result, in which case you go KEQ times 1 over RA, 1 over RB minus 1 over RA. Because there's a minus sign in the front.
Professor?
Yes.
On the top, you can get rid of the minus.
Oh, okay, sorry. Thank you. I have to carry that, yeah. So here's the conclusion. Conclusion is the electrical potential due to a charge is related to 1 over R. So from this point of view, if you take the reference, the voltage or the potential is far away, then that becomes 0. So it all depends on where you're using the reference. Suppose you're using a reference, R sub A is approach to infinity, that's serving as your reference point. So in that case, V sub B is equal to KEQ 1 over RB. From this situation, we can very solidly to say the voltage due to electrical charges can be written as a KEQ divided by R. So that is the point we like to say. Equal to voltage, we will do this experiment. Patient equal to KEQ divided by R. Now, on the section 20.4, if you have a voltage now, electric potential, you can find the electrical field. That means if you have a electrical potential, you can find electrical field. That means you can find E from V. So to find that, we go back to the last point we like to talk about. In that cases is on the section last time, we have D equation 20.3. We say that is dV is equal to minus integration of A divided by B, in this case E dot ds. Go back to the originally, we talk about this again. In these cases, we generally we can simplify as such. dV is nothing but equal to minus E dot ds. Okay, now we want to say if ds is along a line, suppose only along the x direction, then we have dvx, and that equal to minus edx along x direction. Then we have a dvx is equal to edx. So if that is along the x direction, the electrical field is along that direction as well. Based on this mathematics, then we have a E sub x equal to dv sub x dx. So from this simple analogy, so we can say in generally, we can, from the potential, electrical potential, we can come down to find